In 1929, in Chicago, people began dying quietly in their own homes. There were no signs of struggle, no obvious cause, just ordinary apartments with ordinary kitchens, and bodies discovered hours later. It took 15 deaths before the pattern clicked. The culprit wasn't foul play. It was the refrigerator. Fridges weren't just boxes of ice anymore. They were machines cooled by circulating gases. And the standout coolant of the day, methyl chloride, had two fatal qualities. It was toxic and almost odorless. A leak meant you could inhale it without noticing, fall asleep, and never wake up. Other models used flammable gases. One spark near the stove, and a whole kitchen could become an explosive experiment. So a fix wasn't optional, it was urgent. A few years later, a chemical company decided to solve the fridge problem once and for all. In trying to make homes safer, they accidentally created a material that seemed to defy the world's usual rules. That substance slipped into everyday life so completely that within a generation it showed up in cookware, clothing, medical devices, even in the machines that built some of our most advanced technologies. And yet those same innovations came with an invisible price. Chemicals escaping into our water, air, and bodies, and everywhere all at once contamination that no one outside a handful of companies fully understood. This chapter begins at the moment when good intentions collided with the simplest question chemistry can ask. What sticks to what, and what doesn't? In 1936, DuPont put a 27-year-old chemist named Roy J. Plunkett in charge of finding a better refrigerant, something not poisonous, not flammable, and stable enough to behave inside a home. Among the candidates was a gas called tetrafluoroethylene, TFE for short, two carbons double bonded, each bearing two fluorine atoms. One morning, while setting up another routine run, Plunkett's assistant hauled over a pressurized cylinder of TFE, opened the valve, and got nothing. No hiss, no flow. The scale said the cylinder was still heavy, which didn't make sense if the gas had leaked. So Plunkett did something few of us get to do in a lab. He took a saw to the tank. Inside, there was no loose gas. The cylinder was packed with a fine white powder that felt strange between the fingers, slick, resistant, almost oily without being oily. Where had the gas gone? Plunkett reasoned that under high pressure one of TFE's double bonds must have snapped open. That's chemistry's invitation. When you break a double bond, you create reactive sites. One carbon in one TFE molecule can grab another carbon from another TFE molecule, break that molecule's double bond, and keep going. Once that train starts, it doesn't politely stop. The result was polymerization. Countless TFE molecules joined into long chains, polytetrafluoroethylene. A gas transformed into a solid powder. By itself, that ruined the experiment. He hadn't set out to make a polymer. But before tossing it, Plunkett did the sensible thing. He tested the nuisance. Water beat it up and rolled away. Strong acids left it unimpressed. Strong bases didn't melt it. He tried the lab solvents one by one. The dull work chemists do when they suspect they've made something stubborn. Nothing touched it. The powder didn't dissolve. It didn't corrode. It didn't even seem inclined to notice most other chemicals existed. It looked, to use a word we reserve for very few substances, indestructible. The reason sat inside one type of bond that the substance had in overwhelming numbers: carbon, fluorine. Fluorine is the most electronegative element on the periodic table, the greediest for electrons. It wants to complete its outer shell so strongly that, when paired with carbon, it tugs the shared electrons close, making the fluorine side a little negative and the carbon side a little positive. That slight charge separation adds an electrostatic glue to the already strong covalent link. Among the bonds a carbon can form, the single bond to fluorine is the most energetic fortress. To most chemicals, a surface armored with C-F bonds is a wall you don't get through. Plunkett's powder wasn't magic. It just behaved like it. At first, he didn't know what to do with it. A material that refuses to react is impressive, but it's not obviously useful unless you can put it somewhere that desperate reactions happen. DuPont, as it happened, had a very large place in mind. The United States was racing to enrich uranium and produce plutonium for a secret wartime project, and the harsh gas used in enrichment, uranium hexafluoride, 8 gaskets, coatings, and miles of metal piping. If this new polymer could shrug off acids, bases, and solvents, maybe it could keep uranium hexafluoride from chewing through the plant's infrastructure. It could. Compressed under high pressure into solid cakes, machined into rings and liners, the white polymer eased into gaskets, seals, and pipe linings, and simply refused to corrode. Production sped up because maintenance slowed down. In 1944, DuPont trademarked the material. Polytetrafluoroethylene was a mouthful. Marketers reached into the word tetra, took T. From fluoro they took FL, and then borrowed on from the era's wonder fibers, rayon, nylon. Teflon was born. There was a problem, though, and it wasn't small. The same chemical stubbornness that made Teflon useful made it hard to make. If you try to polymerize TFE in bulk, the chain-forming reaction releases heat. If you don't spread that heat out, the system can run away. Above about 200 degrees Celsius, TFE can decompose into carbon and tetrafluoromethane in a sudden, energy-dumping event. In 1944, such a runaway reaction at DuPont's Arlington, New Jersey, pilot plant exploded, killing 2 workers. The challenge was fundamental. You needed a way to carry heat away and keep the reaction calm. Water was the obvious heat sink. Vast heat capacity, cheap, accessible, but TFE doesn't dissolve well in water. Pumping gas into a water vessel means most of the gas sits atop the liquid, while the reaction, once initiated, happens in a concentrated region. Hotspots don't just give uneven product. In this case, they could be deadly. DuPont needed a way to disperse TFE as tiny droplets throughout water so the reaction would begin everywhere at once and the heat would dissipate harmlessly into the liquid. In 1951, they bought a special surfactant acid from 3M, perfluorooctanoic acid, PFOA, inside DuPont, often just C8. Imagine a molecule with a tail that looks like a short run of Teflon, 8 carbons, all fluorinated, ending in an acid head that loves water. Put PFOA in water, and the molecules line up to hide their fluorinated tails from the liquid while exposing the acid heads. The result is the classic surfactant trick. Tiny micelles, little spheres whose interiors are dry. Stir in TFE, and you can tuck the gas into the centers of those spheres. Add initiator, and polymerization begins inside countless droplets at once. Heat is released everywhere a little, not somewhere a lot. No explosion. You end up with a fine dispersion of Teflon, particles suspended in water, rather than a single clump. That dispersion unlocked something more than safer reactors. You could now spray Teflon as a coating. The puzzle then shifted. How do you get something famously non-stick to stick to a surface? Chemists answered with texture and heat. Sandblast or etch the metal to create microscopic roughness. Spray on the dispersion. Heat it so the water evaporates and the PFOA goes off to wherever organic fluorine goes at those temperatures. Teflon doesn't chemically bond to the metal, but as it softens it oozes into the microgrooves. When it cools, it's mechanically anchored. It's not glue. It's a key fitting into a lock. When wartime secrecy lifted, this lab trick walked straight into the kitchen. A French engineer tried Teflon on fishing gear. His wife suggested a pan. The first non-stick cookware arrived, and a nation discovered how good eggs taste when they don't atomize on iron. From there, Teflon coatings and Teflon-adjacent chemistries spread quickly. Carpets and upholstery acquired stain-resistant guardians. Jackets turned waterproof and breathable. Medical implants found a material the body didn't immediately reject. Engineers coated the Statue of Liberty's steel to guard it from corrosion. Even bullets wore Teflon jackets to glide through barrels with less wear. The word Teflon became cultural shorthand for anything accusations couldn't stick to. It was the era when chemistry's promise, clean, slick, modern, felt unambiguously triumphant. But even in this honeymoon period, there were limits and warnings. Heat a Teflon pan into the 300+ degrees Celsius range, and stray polymer fragments can decompose, giving off fumes that make people feel fluish for a day or two. Polymer fume fever. Birds, with their exquisitely efficient respiratory systems, can die. The lesson wasn't ban the pan, it was don't abuse the pan. A reminder that even inert materials can behave differently at high temperatures. None of that hinted at the problem that would eventually define the story. Teflon itself, the long polymer chains, are so inert that if you ingest flakes, your body mostly ignores and excretes them. The hazard didn't come from the polymer. It came from the small fluorinated molecules used to make and process it, those surfactants and cousins, PFOA, PFOS, and later replacements. Chemically, they looked like fatty acids with hydrogens swapped for fluorines, which meant they could hitch rides on the same proteins that shuttle fats in the blood. Biologically, that opened doors. Their carbon, fluorine armor meant once they were in, nothing in a human enzyme toolkit broke them down quickly. They were durable in pipelines and durable in people. Inside the plant, engineers measured, monitored, and convinced themselves they understood safe limits. Outside the plant, waste had to go somewhere. In the mid-century industrial imagination, somewhere often meant the river, the air, or a landfill lined in ways we now recognize as inadequate. The polymer industry in general, and fluoropolymer manufacturing in particular, weren't unique in that attitude. They were emblematic of it. None of this was obvious to the ordinary consumer savoring scrambled eggs that slid out of a skillet. From a householder's point of view, nonstick cookware just worked. Stain-proof carpets made cleanup easier. Performance fabrics kept you dry. The customer saw convenience. Manufacturers saw market share and revenue. Regulators saw a sector delivering what people wanted. And the chemistry? The chemistry saw every new surface as a place to demonstrate the peculiar magic of flooring. How to make a bond so strong the world bounced off of it. That strength is part of why these chemicals felt like a revolution. Fluorine's small size lets its nucleus pull shared electrons closer than bulkier atoms can. Pack enough fluorines around a carbon chain, and you make a shield. Water beads up, oils spread thin, oxygen molecules can't easily begin the chain reactions that lead to burning or rot. Many of the 20th century's great conveniences ride on those physical facts. The same logic gave us refrigerants that no longer killed people in their sleep, though the path from methyl chloride to modern coolants ran through several generations and their own environmental lessons. It gave us materials that could handle acids that once chewed through metals. It gave us seals that kept the worst actors in industrial chemistry inside their pipes instead of in the world. Still, every technological story eventually asks, where does the away and throw it away actually lead? While Teflon conquered kitchens and climbed into rain jackets, plants kept buying drums of C8 because it made the manufacturing work. The thinking was tidy and internal. Use what you need, keep exposures low, manage waste streams by the standards of the time. But surfactants are built to move between worlds. Oil and water, hydrophobic and hydrophilic, one domain to the other. You can't be shocked, in hindsight, that they found pathways out of factories and into soils, streams, and eventually taps. By the late 1940s and early 1950s, DuPont engineers had learned, painfully, how to prevent reactors from blowing. By the mid-1950s, the kitchen miracle had a brand and a marketing plan. By the 1960s, internal toxicology reports began to note that some of the small fluorinated acids weren't benign at high doses in animal studies. That evidence stayed mostly inside file cabinets. In those years, industry wasn't set up to publish everything it learned about hazards that might crater a product line. The machine kept moving because the products kept selling and because, important to say, the majority of people working on them believed in the project. Make life safer, cleaner, easier. If part 1 is about discovery and promise, the cylinder cut open to reveal a powder that resists the world. Part 2 will be about what happens when a molecule designed to resist the world meets the actual world. The next act starts far from a lab bench, down a creek where cattle stopped eating, with a man who filmed what he saw because no one believed him. Before we get there, hold on to the properties that made all of this possible. The extraordinary strength of the carbon-fluorine bond. The way surfactants ferry substances between places that should not mix. The human habit of assuming that if something is useful in one domain, it will behave in every domain. Those 3 threads will braid together into the shape of a scandal, and the global cleanup problem we now call forever chemicals. Because the same chemistry that kept poison gases out of kitchens and uranium hexafluoride inside pipes also kept certain small, fluorinated acids alive and moving once they escaped. They didn't burn. They didn't rot. They didn't break. They just kept going into rivers, into aquifers, into tap water, into blood. And at first, almost no one outside the companies making them had the tools or the context to notice. That part of the story doesn't begin with a breakthrough. It begins with a discharge pipe and white foam where it shouldn't have been, and a stack of VHS tapes dropped on a lawyer's desk with a simple, stubborn claim. Something in this water is killing my animals. On a small farm outside Parkersburg, West Virginia, a cattleman named Earl Tennant began to notice changes that don't belong in fields. Animals that once trotted to the trough standing still, not eating, eyes dull, coats roughing out as if winter had moved inside their bodies. Calves wasted, full-grown cows turned to bone. Some had tumors you could see without wanting to. Others died without warning, as if an invisible hand had pinched shut the line between breath in and breath out. Earl did the thing practical men do when reality stops behaving. He paid attention. He followed the creek that ran through his pasture back to where it entered his land, and then farther, to the fence line he couldn't cross. On the other side stood the Washington Works complex, DuPont's first commercial Teflon plant, a dense city of pipes, towers, and steam where chemistry lived at industrial scale. Between plant and pasture sat a landfill. Out of the landfill ran a discharge pipe. And out of the pipe, on too many days, poured something the creek hadn't asked for, white foam. In the videos Earl shot, grainy camcorder frames, the kind you can almost hear when you look at them, you can see that foam crawling across water like soap freed from dishes. Cows step through it. Their hooves look raw, hairs at the fetlock eaten down. Fish don't bother to flee. They're already elsewhere. Earl's voice on the tapes is not theatrical. It's the cadence of a person who needs a record because saying it out loud hasn't worked. If chemistry is the discipline of what sticks to what, this foam stuck to Earl's life. When he tried to tell people, they edged away. Parkersburg is a company town in the old American sense. The plant doesn't just provide jobs. It fields the softball team, sponsors the picnic, funds the culture center, fixes the road. To say the plant is poisoning your herd is to announce in public that the sun has turned on the town. Earl's family learned the choreography of the cold shoulder. A roomful of neighbors pushing chairs back, then the door. So he did the next practical thing. He found a lawyer, someone who wasn't part of the town's gravity well, drove to a Cincinnati office, and set the tapes on a conference room table. The attorney, Rob, didn't begin as an activist or an enemy of industry. He was a corporate defense lawyer, fluent in stacks of documents and the ways companies organize their choices. He took the case because the videos looked like evidence, and evidence is the language the law understands. The official route in a matter like this is straightforward on paper. The Environmental Protection Agency decides which chemicals you're allowed to put in a landfill and how. There are permits. There are records. If something illegal is being dumped, the paperwork should betray it. Rob requested the Washington Works operational files, the waste manifests, the internal memos, the lists of substances moving in and out. When a company tries to bury a case, it often buries you in paper. DuPont sent more than 60,000 pages. This is where most stories like this quietly stop. A year passes. 2. The boxes gather a dust that starts to look like part of the decor. But Rob wasn't looking for a perfect narrative. He was looking for repetition. What recurs when you sort documents by author, date, scope, and subject? You can learn a lot from the way a word clusters with itself. One term kept surfacing in places that weren't about patents or brand names. It appeared in lab reports and waistline diagrams. It appeared in emails you could tell were written on a clock someone couldn't ignore. Sometimes it showed up as PFAS. Sometimes as perfluorooctanoic acid. Inside DuPont it was often called C8. 8 carbons, all buttoned up with fluorines, with a carboxylic acid at one end to play nicely with water. C8 wasn't the polymer. It wasn't the Teflon in your pan or the liner in a pipe. It was a processing aid that made the polymerization behave. The thing that surrounded tiny droplets of TFE in water, kept the reaction cool, and let you spray a non-stick miracle as a coating. A soap without bubbles, a ferry boat for gases. On paper, C8 looked like a cousin to the fatty acids every mammal uses. Except everywhere a fat would have hydrogen, C8 had fluorine. That substitution was chemistry's equivalent of forging steel from bone. You keep the shape that fits biological machinery, but you swap the stuff that breaks down for stuff that doesn't. The result is a molecule that can ride the same proteins fats used to move through blood, cross the same membranes, visit the same organs, and then refuse to leave. Nothing in our enzyme catalog pulls a carbon-fluorine bond apart on schedule. The story of what DuPont knew about C8 doesn't fit in a single memo. It unfolds over years. Rats tested in 1961 and found with swollen livers at tiny doses, some dead at higher ones. The study repeated in 1962 with the same direction of harm. Dogs in 1965. Later, monkeys. Each species added a line to the same uncomfortable chorus. At certain doses, this compound is toxic. Inside the company, the language adjusted itself the way language does when the truth crowds the room. Materials should be handled with extreme care. Contact with skin should be strictly avoided. These weren't press releases. They were instructions for workers. There was a second thread. In the 1970s, public health researchers studying fluoridated drinking water measured blood and found, no surprise, more inorganic fluoride where tap water had more fluoride. But there was also a signature of organic fluorine, carbon-fluorine bonds, that didn't track with the water additive. The scientists approached 3M to ask if their fluorochemicals could be the source. If you read the correspondence, you can see a company doing what companies do when a question aims at the bottom of a cash register. Wait, study internally, report conservatively. 3 months later, 3M had compared spectra and found a match. Their chemicals were showing up in people's blood. That fact, for the moment, stayed in-house. Around the same time, both 3M and DuPont tested their own workers. If you want to know whether a molecule is getting from the line into people, you look at the people next to the line. The levels they found were not subtle. In some plants, the concentration of C8 in workers' blood ran 1,000 times higher than the background the population carried. Medical charts showed an uptick in liver issues. You can picture the meetings, good people who needed to keep a plant producing, looking at charts with bad shapes. Meanwhile, the waste had to go somewhere. Washington Works dumped roughly 10 tons of C8 into the Ohio River each year and piled thousands more tons in a landfill where the chemical could leach out. Guided by gravity's patience, toward whatever lay downhill. On TV, the company aired a commercial assuring the public the water was collected and tested to keep pollution out of the Ohio. Both statements can be true at once and still miss the point. You can test a lot. You can miss a lot, especially when you don't yet have a robust way to detect what you're not quite admitting you should be looking for. By the early 1980s, a rat cancer study put the hazard in a form no one likes to see in print: tumors, including testicular. If you've ever watched an organization absorb information it cannot use without injuring itself, you know the moves that follow. DuPont convened officials in 1984 to ask whether C8 should be replaced. There were alternatives in view, but none that looked as cheap or as effective for the fine powder business. The conclusion on paper reads almost like a stage direction. Currently, none of the options are economically attractive. You can hear the meeting end with a sigh and the ritual rub of tired eyes. So they did something that felt prudent at the time and looks different in the rearview mirror. They set an internal number for what would count as safe in drinking water. Their scientists estimated 0.6 parts per billion and, for simplicity, rounded to 1. Chemistry loves precision, but commerce loves round numbers. 1 ppb had another advantage. Back then, it sat near the practical detection limit. If you can't measure it, you can't be out of compliance. The math felt neat. The world is not neat. When DuPont sampled the wastewater flowing from the landfill into Earls Creek, the number came back a long way from neat, around 1,600 parts per billion. The number did not appear in a public advisory. It appeared in documents Rob would eventually read, pen-scratching notations in the margins that changed from tidy to urgent. He built a letter, a tome, really, 900 pages of citations and cross-references, a map from foam on a creek to molecules in a blood sample to memos about dosing rats. He sent it to the EPA, to the Department of Justice, to the U.S. Attorney General. Within months, DuPont settled with Earl and his family for an undisclosed sum. There was no admission of wrongdoing. There rarely is. The settlement answered one household's crisis and left untouched the more frightening shape of the problem. Because if C8 could walk from a landfill into a creek and into cows, it could walk other paths too. Into aquifers, into taps, into people who didn't know enough chemistry to suspect there was such a thing as perfluorooctanoic acid, and who didn't need to know until now. Rob filed again, this time on behalf of tens of thousands of people around Parkersburg whose water likely carried C8 for decades. That's where the story widens. The creek was never just a creek. Reading through the records, you see how normal it all must have felt from the inside. In 1961, when that first rat study rang its quiet bell, the United States was still new to the bulk manufacture of miracles. We were learning in real time how to have plastics without catastrophe, solvents without stupor, accelerants without fire. Every industry was adjusting its definition of acceptable risk. A toxicology report was data for better handling, not necessarily a verdict to shut down a product line. Regulations existed, but their networks were thin. The instruments at the time could not reliably detect parts per trillion in environmental water. The scientific literature on long-chain perfluorinated acids was sparse and mostly behind corporate walls. And when a material is both profitable and trusted by everyday people, pans that changed how you cook, jackets that changed what rain means, the path of least resistance is always forward. And yet, outside the plant, the material behaved exactly as designed. It moved between phases that weren't supposed to mix. It clung to proteins built to carry fats. It ignored the breakdown pressures that remove most human messes from the stage. It accumulated, not quickly enough to panic anyone in a week, not slowly enough to be irrelevant over a decade. If you were living in Parkersburg in those years, you likely tasted none of this. Water tasted like water. The cups sweated on the porch the way it always had. The point of the carbon-fluorine bond is that the world does not notice it. That's what made it powerful in a gasket and invisible in a glass. Rob is not the hero of a movie here. He is a person who reads for a living and noticed that the same acronym kept saying hello from different corners of a file room. He had a client who needed an answer about dead cows in a town where every third person knew someone who wore a DuPont badge to work. You don't expose a chemical cover-up by standing on the steps and shouting. You do it by walking back and forth between a factory's definition of acceptable and a creek's definition of alive, until you can plot the overlap in a way both a judge and a person at a kitchen table can feel. There is a detail from the farm that doesn't leave you. On one tape, a cow stands shin-deep in white, as if a storm had laid down a snow that only the creek could see. Earl films without commenting for a few seconds too long, and the silence is the comment. No geese. No insects fussing. Just water moving around a surface that has forgotten how to be water. Zoom the frame out. The same chemical that helped prevent explosions in a reactor had learned to keep its promises in a valley. The same surfactant that let a miracle polymer spread evenly across a pan was easing a perfluorinated acid into systems that couldn't metabolize it. The same production line that made non-stick coats for bullets and rain gear also made a waste stream that walked, over years, into a man's pasture where the only alarms available were hooves and eyes. If part 1 was the discovery of a powder that didn't care, part 2 is the discovery of what that not caring looks like when it leaves the lab. It is also the moment the story outgrows one farm. Because C8 didn't learn to travel only in West Virginia. Around the turn of the millennium, independent studies drew blood in cities far from Parkersburg and found that nearly every American carried measurable amounts of C8, averaging around 5 parts per billion then. This wasn't a localized poisoning in the way smokestacks once were. It was diffusion as a way of life. The people most exposed were those closest to manufacturing or firefighting foams that used similar chemistries: workers, soldiers, airport crews. But the whole distribution curve shifted. The baseline for normal included molecules our grandparents didn't host. If you want to see the 21st century in a number, look at the part per billion levels of compounds no one had a name for at the breakfast table. None of this turns the white powder from part 1 into a villain. Teflon, the polymer, remains what it is. A chain so inert your body more or less shrugs at it when it arrives as a flake. The problem is the entourage, a family of small, persistent fluorinated acids we later grouped under the umbrella PFAS, of which PFOA is maybe the most famous older cousin. In the making of miracles, you invite assistants into the room. The assistants learn more of the building's layout than you do. Earl and Sandra Tennant didn't live to see the full arc of the case their farm began. Many of the people who gave blood and wrote down their symptoms for the massive medical study that followed didn't either. That study, the one that would later link C8 with a handful of human diseases in a way the courts could accept, belongs to a later chapter. Before we get there, the narrative spends time in a place most viewers skip if you give them a progress bar: the document room, the years, the way a town recalibrates its trust in a company that sponsored its children's teams. There's no montage you can play over this interval to make it shorter. What there is a pivot. The moment a case about cows becomes a case about people. The moment a number on a memo, 1,600 parts per billion, stops being a curiosity and becomes a map pin. You can draw a line from the discharge pipe to the creek to the farmhouse well to a cup. You can draw another line from the plant to air stacks to rain to soil to another cup somewhere you didn't expect. It's chemistry, but it's also cartography. After the second lawsuit, the story stopped being about one pasture and a few dead cows. It became about tap water, blood levels, and the long stretch of time during which no one thought to look. People in the water districts around Washington Works had been drinking from the river for years. No one measures what they aren't searching for. Now they had to search. The usual legal routine could have dragged on for years, arguing about liability, battling over experts, ending with a quiet settlement. This case didn't fit that pattern. The chemistry was unfamiliar to most people. The exposure unfolded over decades, and the health outcomes were not the kind you can sum up in a neat sentence. So the plan shifted. First, generate facts, then argue about conclusions. The company agreed to fund a large community health project, not as a publicity exercise, but because there was no other way to prove or disprove what people suspected. Letters went out to towns and unincorporated areas. Temporary clinics opened in schools, rec centers, and union halls. Families showed up together. They filled out forms about their water sources, jobs, habits, diagnoses, and medications. They rolled up their sleeves and waited while a nurse labeled vials. Then came centrifuges, coolers, courier routes, lab procedures. What began as a reaction to foam in one creek slowly turned into one of the largest health portraits in the country, focused on a single group of industrial chemicals. Each tube of blood answered two basic questions: how much of the fluorinated compounds were present, and what medical conditions traveled alongside them. On average, residents in the affected water systems carried higher serum levels than the national median at the time. Averages don't tell a life story. Connections do, and real connections take time. Researchers had to pull apart age from habit, work from genetics, a resident's history from a medical history. They could not assign one town clean water and another contaminated water the way a drug trial assigns a pill. They could only rebuild the past as faithfully as possible and see which pairings appeared more often than chance could explain. Time moved slowly. Some of the people who gave blood and told their stories did not live to see results in print. For the town, the wait was not abstract. For the plant, operations carried on under familiar assumptions while the math ran its course. For households, daily life stayed the same. Open the tap, put a pot on the stove, do what you have always done because the alternatives are not ready yet. Along the way, everybody had to learn a new language. Residents learned to separate the polymer that barely reacts with anything from the smaller fluorinated acids that helped make it. They learned units that used to belong only to lab reports, parts per billion in blood, parts per trillion in water, and how those numbers relate over years rather than days. Undetectable no longer meant absent, and present did not automatically mean dangerous. Somewhere between those poles, a new kind of responsibility took shape. Water systems began to change. Some utilities added treatment trains. Kitchens filled with pitchers and undersink units. There were no grand gestures. People quietly altered routine. At public meetings, terms that once lived only in engineering binders entered everyday speech. Granular activated carbon, ion exchange, breakthrough curve, media changeout. The vocabulary was technical because accuracy required it. Inside the plant, the conversations never stopped. Supply chains, customer specs, reactor settings, cost models. You do not swap out a process aid overnight. Sometimes you have to re-qualify products for demanding buyers, retune equipment, and accept higher costs. That is not an excuse. It is one reason changes rarely happen instantly, even when everyone understands that the old way is over. When the independent panel released its conclusions, the language was careful and plain. For several conditions, long-term exposure to the fluorinated acids showed probable links. The list included high cholesterol, thyroid disease, pregnancy complications involving high blood pressure, and 2 cancers, kidney and testicular. Other conditions did not meet the panel's criteria at the time. That did not mean they were disproven everywhere forever. It meant this dataset, analyzed under this method, did not support a link strong enough to name. Those findings opened a doorway in court. People with the qualifying diagnoses could bring individual claims backed by community data rather than only personal testimony. For the broader public, what mattered most was simpler. At last, there was an evidence-based answer to the question that had been hanging over kitchen tables since the first rumors. What does this mean for me and my family? There was also the outline of a method other towns could adapt if they ever had to. Enroll widely. Measure exposure and outcomes with care. Put the analysis in independent hands. Say in advance what counts as a finding. While all this was grinding forward, the country learned a new term, forever chemicals. It appeared in newspapers, on local TV, in the water utility newsletter that ends up rubber-banded to a doorknob. Not because of a single dramatic report, but because many separate pieces finally lined up. Internal technical notes, animal studies, worker biomonitoring, community epidemiology, environmental sampling, treatment feasibility, and cost. Each part by itself was incomplete. Together, they made it harder to keep the old assumptions. Local trust took longer to mend than a standard or a detection method. The plant was still a key employer. The company still sponsored teams and events. Plenty of households still depended on paychecks tied directly or indirectly to fluorochemistry. That dual reality set the tone in churches, school parking lots, and grocery aisles. People can hold two truths when they have to. This job pays my mortgage. This company handled part of its business in a way that harmed my neighbors. Even after new filters went in and water sources shifted, blood levels did not plunge. These molecules linger in the body longer than most pollutants, so the slope downward takes months and years. For pregnant people and infants, timing matters. For firefighters, the questions were occupational. Gear and foams had their own profiles. What could be changed in equipment, and what actually works to lower exposure? Small studies hinted that frequent blood or plasma donation can reduce certain PFAS levels in high-exposure groups, but medical advice remained cautious and case-specific. Industry, meanwhile, began changing formulas. The 8-carbonate that had been central to the process disappeared from many lines. Shorter-chain alternatives and other variants took its place. On paper, those molecules promised to move through bodies faster and build up less. In practice, the picture was mixed. Some did clear more quickly, yet spread more easily in the environment. Toxicology on replacements lagged deployment. New acronyms entered the public vocabulary only after they had already reached the watershed. For residents, daily life settled into a simple discipline. Read the notices. Look at the numbers in the water reports. Change filter cartridges on schedule. Ask clear questions at community meetings. Vigilance became habit. Habit became the local norm. Where utilities explained why a project would take a year and what people could do in the meantime, confidence held. Where updates stayed terse and technical, rumors did the talking. Companies drew an old lesson in a new setting. Anything you use to make a product is part of the product for the purpose of risk. If a chemical is essential, keep it contained, measure what escapes, and react to changes with actions rather than memos. If a chemical can be replaced, build the case for the replacement before you scale it, not after. It is slower now and cheaper later. Parkersburg did not become a symbol to pity or a place to forget. It learned how to live forward while knowing more than it wanted to know. People still keep the plastic wristbands from their blood draw days. They still talk about utility updates in the checkout line. Some still work at the same plant and do not pretend complicated issues have simple answers. The town did not ask for this role, but it played it well enough to help other places learn how to turn worry into procedure. During these same years, measurement sharpened. What got lost in noise a decade ago now shows up as a clean signal. Maps that once showed a few dots began to fill in. Airports and military bases lit up as distinct sources because of firefighting foams. Manufacturing clusters on several continents appeared with similar patterns. This does not mean every place is affected the same way. It means the phenomenon is systemic, which changes what counts as a sensible fix. At the household level, advice stayed practical rather than dramatic. If your water system has documented PFAS, use certified filtration for drinking and cooking or a different source. Avoid heating food in grease-resistant packaging. Keep up with utility testing schedules and results. Talk with your doctor if you are pregnant or work in a high-exposure job. None of this solves the whole problem. Together, steps like these reduce the load over time. At the city level, engineers folded PFAS removal into normal design work. They chose between granular activated carbon, ion exchange, and reverse osmosis based on local water chemistry and budgets. They sized vessels sensibly, modeled breakthrough, planned media changeouts, and put the costs into operating plans. It sounded like shop talk because it was. That is how public health usually improves once headlines fade: standard operating procedures, maintenance logs, and budget lines. At the state and federal level, definitions and limits tightened. Advisories turned into enforceable standards in some places. Methods were standardized so numbers could be compared. As limits for key compounds dropped into the parts per trillion range, utilities had to decide whether to retrofit, build new trains, or blend sources. Those choices took time, money, and politics, and they demanded plain communication to keep people on board. In homes and offices, and at the plant gate, the topic stopped feeling like a mystery and started feeling like a set of tasks. Test on schedule. Publish results in language the public can use. Install the equipment you said you would install. Replace the media when it is due. Keep teaching new staff what the last group learned the hard way. None of this is a victory lap. It is what living with a resolved argument looks like. Years earlier, company documents had carried flat sentences about careful handling, avoiding skin contact, toxic effects at certain doses. They were written for internal use and filed away. Now similar sentences appear in public-facing materials read by people who have no use for corporate vocabulary, but who know how to take care of their kitchens, their water, and their town. Maybe this is what learning looks like when it sticks. Not a slogan on a billboard, but the steady habit of turning on a tap with a clearer idea of what that action means. By the time the community results were out, the plant had already been living with a different question. If the old processing aid could no longer be the way forward, what would take its place, and what would that change in practice? Chemists do what chemists do when the brief is same function, fewer consequences. They trim chains, break patterns, add an oxygen here or there, and wager that a shorter, slightly different molecule will move through the world more quickly and linger less in a body. On the whiteboard, the logic was tidy. Shorter chains tend to bioaccumulate less. Tweaks in structure can change how proteins recognize a molecule. If it clears faster, the long tail and blood curves downward sooner, and the next set of charts looks better. On paper, that meant a new processing aid would stand where the 8-carbon workhorse had stood for decades. In the plant, it meant purging lines, revalidating recipes, and convincing the customers who needed absolute consistency that nothing they cared about would change. In the town, it meant the old acronym fell out of casual conversation and a new one took its place. People kept the same questions. What is in the river now? What are we breathing, rinsing, boiling, pouring into ice trays? If the lab can measure it, will the utility publish it? If the utility publishes it, will the number go down next quarter or next year? Early on, the promise of the replacement carried more hope than proof. Animal toxicology takes time. Epidemiology takes longer. Meanwhile, a river does not wait. Downstream communities began to watch their own taps the way Parkersburg had watched theirs, and maps that once had one cluster of colored dots began to add another hundreds of miles away. If you lived there, you learned the story in the usual way. A local headline, a meeting at a high school gym, a printed FAQ about sampling schedules and interim filters, the audible patience in a city engineer's voice as he explained what breakthrough means when you're staring at a carbon bed that has done its job for months and now needs to be changed. The replacement did behave differently in blood. In people who were exposed, levels tended to fall faster after the source water changed or a filter went in. That was the point of the redesign. But the same features that let the new molecule move out of bodies more quickly helped it travel farther in the environment. It slipped through soil and sand in places the old aid would have held back. It crossed into smaller streams and then larger ones. It showed up in intakes you would not have thought to sample a decade earlier. The trade-off had always been there in the chemistry. It simply came into view at human scale. Utilities learned that the tool you choose depends on the water you are treating and the molecule you are trying to stop. Granular activated carbon that chewed the problem down neatly in one town did less in another with a different replacement profile. Ion exchange resins that grabbed short-chain molecules needed careful regeneration plans and waste handling. Reverse osmosis took almost everything out of the finished water but left a concentrate that had to be managed so the problem did not just move downstream. Engineers began to speak about PFAS not as a single issue, but as a moving front that required a portfolio, a schedule, a way to keep up with the river rather than pretend you could get ahead of it forever. Far from these rooms, another kind of meeting was happening on airport tarmacs and at fire academies. For decades, the foams used to smother fuel fires owed their effectiveness to the same class of chemistry. Lower the surface tension, spread quickly, block oxygen, stay put. On a runway or in a training pit, that performance is not an abstraction. It is the difference between a controlled burn and an event. As the industry turned away from legacy formulations, departments inventoried stockpiles, wrote new standard operating procedures, and trained on fluorine-free foams that behaved differently in the field. Crews learned to adjust nozzle patterns, application rates, and technique. Decontamination practices changed. Turnout gear was reevaluated. The work was incremental and practical, and it often came with a quiet recognition that the foam that had kept people alive had also been walking into groundwater for years. Inside factories that never draw a crowd, the conversation was even less visible, but just as direct. Some processes still needed fluoropolymers that don't burn, don't swell, don't react, and don't shed particles in places where particles ruin the day. Medical devices that sit in the body for years need surfaces that do not tempt inflammation. Pharmaceutical and vaccine production relies on tubing that does not leach. Semiconductor lines need seals and coatings that tolerate harsh chemistries without adding their own contaminants at the parts per trillion level. No one wants a pacemaker to fail or a chip wafer to be ruined because a gasket could not take the bath. Where a fluorinated material was genuinely essential, the mandate sharpened. Keep it in a closed loop, capture emissions at the stack, capture residuals in wastewater, measure aggressively, and prove it with numbers your neighbors can read. Destruction became a word people used more carefully. Burn something like this at the wrong temperature or with the wrong residence time, and you risk trading one problem for another. Thermal units were upgraded, monitored, and audited to keep the chemistry on the side of completion rather than conversion. Contracts with off-site handlers were rewritten to require the same discipline. The market for capture media grew. So did the responsibility to handle the captured load as the hazard it is, not as an inconvenient sludge to be shipped out of sight. In laboratories, methods tightened. The instruments that once struggled to see parts per billion in water now made routine work out of parts per trillion across dozens of compounds. Labs built catalogs of retention times and fragment ions the way birders build field guides. With each new run, the fingerprint of a place became clearer, which species dominated, how they changed with season and treatment, whether a new upstream source had quietly switched in a different aid and left its signature on a chromatogram. Because the methods were standardized, numbers in one report could be set next to numbers in another without arguing over how the measurement was made. That made public meetings less about whose lab to trust and more about what to do next. At kitchen tables, the learning was practical. People stopped reheating food inside the grease-resistant packaging, not because a single bag would upend a blood test, but because doing the simple thing over and over changes the baseline. Some households put a small note on the calendar to remind them when to change a filter. Some chose cookware that matched their comfort with heat and coating and learned the quirks of stainless steel or seasoned cast iron. Some kept their nonstick pans and used them reasonably because the polymer itself was not the villain and the birds on the windowsill mattered more than a theory. The point was not to live a lab manual. The point was to bring a little more intention to a handful of routines. The broader water cycle came into sharper relief. What fell as rain in one county did not necessarily start there. Clouds gathered moisture over catchments that included airfields, plants, and highways, and the chemistry that made a foam spread also helped traces ride aerosols. Snowmelt brought legacy loads out of soil and into creeks with the first warm days of spring. Reservoir levels fell and rose and diluted and concentrated depending on a given year's heat and drought. Utilities adjusted blending. Sampling schedules shifted to match seasonal realities rather than calendar quarters. The invisible turned out to have seasons. In states and countries that moved faster, the numbers in law fell to levels instruments could see and utilities could meet. Where the limits stayed advisory, a few local boards adopted their own targets and built projects to hit them. Politics did what politics does, argued over timelines and costs, and engineers did what engineers do, built the thing. The new vessels did not announce themselves as victories. They sat behind chain link and did their jobs, the way most progress looks when the ribbon cutting ends. Workers learned that a clean process protects them first. Air monitors went up in places that had never had them. Personal protective equipment changed in ways that were boring to outsiders and important to the people who wore it. Hygiene practices around powder handling got stricter. Smoking areas moved farther from places where residue could hitch a ride. The old signs about avoiding skin contact finally felt less like wallpaper and more like habit. Programs to test blood at certain job sites moved from pilot to offered annually, and the numbers came down when the rest of the system did. Communities that had never heard of any of this a few years earlier now recognized the pattern as soon as it began. White foam did not need to show up for a town to take notice. A permitting notice in a small legal ad could generate a dozen emails to a council member in a day. Local reporters got better at covering the story accurately without pushing panic or apathy. When a consultant stood at a lectern with a slide about resins and beds and change-out intervals, people understood what they were looking at. When a lawyer stood up to say that any settlement should include funds for monitoring and medical follow-up, people understood why that part mattered as much as a check. All the while, the products that started this journey kept doing the jobs that made them valuable in the first place. A valve with the right seal still saved a batch and a day. A jacket kept someone dry on a freezing morning. A catheter did not irritate. A wire was insulated against the heat it would not have survived otherwise. The question shifted from, is this substance good or bad, to, where does it belong and how do we keep it there? If a molecule was going to be built to last, then the system around it had to be built to hold it. Some companies moved faster than others, and some found themselves explaining past decisions in present tense. In boardrooms, the risk slides no longer stopped at lawsuits. They included line items for retrofits, ongoing monitoring, community engagement, product reformulation, and the very real advantage of not having your brand show up on a map of contamination points. In procurement, available at scale and meets spec had neighbors now, demonstrated fate profile, and tested capture. The same discipline that once went into choosing a catalyst went into choosing a supplier. An industry that prided itself on precision began to extend that culture beyond yield and into consequence. This was never a single company story. Plants in other states and on other continents went through versions of the same cycle, sometimes ahead, sometimes behind. Airports and bases had their own timelines, their own inventories to work through, their own training calendars to change. Towns that never made a pound of fluoropolymer nonetheless became part of the map because water does not read company names on invoices. In a way, that made the conversation easier. Once a pattern is systemic, solutions can be shared more honestly. You do not have to pretend your situation is unique when everyone knows it isn't. At home, the topic stopped feeling like a scandal and started feeling like maintenance. The noise on social media quieted to a hum. The useful voices remained. The utility account that published monthly graphs. The nurse practitioner who posted a plain explanation of what a blood test can and cannot tell you. The firefighter who wrote about gear changes in a way recruits could absorb. The teacher who used a simple experiment to explain surface tension and why a foam spreads. One by one, the pieces of knowledge that used to belong to a handful of specialists turned into shared literacy. If there was an emotional shift, it was small and steady. Fear gave way to attention. Attention gave way to competence. Competence made room for the kind of calm that lets a town make decisions without false urgency or denial. No one forgot the old story. They simply made it part of the manual and carried on. Most of what people learned next did not come from courtrooms or labs. It came from kitchens that had to keep working. A home is a small factory with water in and waste out, heat applied in between, and 1,000 tiny choices that add up to a pattern you barely notice until you decide to change one. When neighbors compared notes, they weren't trading theories. They were trading habits and the small outcomes that follow from them. Water was the plainest place to start. If the utility had added treatment, the tap tasted the same but carried a different story. Where a household added its own filter, someone put a date on the cartridge with a marker, then learned to tell by feel when the flow had slowed. A few families who tried bottled water for everything drifted back to filtered tap for cooking because hauling jugs in August did not feel like a solution. People settled into rhythms that balanced effort with effect. No one was chasing a perfect number. They were trying to be a little less careless than before. Cooking turned into a quiet experiment. Stainless steel behaved if you heated it long enough and then backed the flame down before the onions went in. Cast iron remembered what you cooked last week and rewarded you for not scrubbing away its memory. The nonstick pan stayed in the cabinet for eggs on a tired morning, handled with the kind of respect that keeps birds alive and air easy to breathe. It turned out there was no single correct answer because there had never been a single correct kitchen. People found the tools that matched their patience and their stove. Packaging was a lesson in temperature. The same takeout box that safely carried dinner across town did not need to be a microwave tray. The grease-resistant paper that had seemed like a favor to the customer became something to set aside once it had done its job. Food went onto plates and into glass containers before reheating. A tiny change that, repeated enough times, moved the baseline. Popcorn was a reminder that a bag in a pantry is not a neutral place. The smell that made the kitchen feel like a movie night came with a chemistry you could avoid by shifting the ritual to a pot and a lid. Once you learn the rhythm, oil first, a few kernels to test, the clatter that means it's time, you didn't need the bag. Dust had its say. Things that drift onto floors and shelves are a record of what your life sheds and what the air carries in. Vacuuming with a decent filter mattered more than anyone expected. A damp cloth did the rest. No one made a religion out of it. They just noticed that the house is part of the cycle, not separate from it. Shoes stayed by the door more often. Small habits stuck because they were simple and because they didn't ask for a lecture every time you did them. If there was a surprise, it was how much of exposure is not dramatic. Most of the load that ends up in a person is background plus time. That can make the problem feel unsolvable until you flip the same equation over and notice that small changes, done often enough, also add up. A household that switches to filtered drinking and cooking water, reheats food on plates, and keeps a practical cleaning routine will see its numbers drift downward when the town's numbers do. It is not a headline. It is a slope. Jobs mattered. People in high-exposure work learned to treat gear and procedure as part of health, not just safety. Firefighters who had spent years trusting a certain foam trained on the alternatives and learned to make them work because no one wants a truck on its side or a jet with fuel burning wrong. Decontamination was not a chore to delay anymore. It was the last step that made the shift real. In other places, plating shops, fabrication lines, labs, managers added monitors and air changes and wash stations. A handful of small decisions, enforced every shift, made more difference than a poster ever did. Pregnancy changed the stakes without changing the tools. Prenatal visits started to include a conversation about water source and filtration the way they already included food and supplements. People who were nursing learned that a filter changes more than taste and that blood thins a little when you give it away. A few of them donated plasma because it helped someone else and, in some cases, lowered their own numbers over time. None of that came with guarantees. It came with a sense that you were not completely at the mercy of the map. Maps improved. The dots grew denser, not because the world got worse all at once, but because instruments learned to see what they had been half blind to before. A county that looked clean with one method showed a faint line with another. Where utilities published raw data rather than summaries, residents read them like weather reports. When an intake switched to a different source, you could watch the graph bend. When a media bed reached breakthrough sooner than expected, you could watch the next month's report show the fix. Public numbers became a way for a town to narrate its own competence. A few myths fell away. Throwing out every nonstick pan in a rush turned out to be theater more than medicine. People learned that the polymer is not the same as the aid that helped make it, and that treating a tool properly is nearly always better than buying a different one poorly suited to how you actually cook. Panic softened into practice. So did denial. We've always done it this way gave way to, we can do this part better, which is about as much reform as most kitchens or plants can sustain and still keep the day moving. There were days when the topic went quiet. Nothing new had been sampled. The filter wasn't due. The inbox didn't have another newsletter with a graph and a paragraph. Those days mattered too. They let the subject stop being a crisis and start being part of how a place understands itself. You could go a week without thinking about water and still be a person who cares about water. The measure of progress was not how loud anyone sounded. It was how much less performative everything had to be. Elsewhere, the same pattern replayed at different scales. A city that drew from a reservoir moved toward new limits without drama, announced the bid for vessels and media, and built what it said it would build. A base counted drums, staged take-back events for old foam, rewrote manuals, and retrained crews. A manufacturer that claimed a new, shorter aid was better found itself explaining why traces of it showed up in groundwater farther away than expected. The answer was honest chemistry. Mobility without persistence in blood does not mean mobility without reach in the environment. Everyone adjusted their mental models and their treatment trains and moved on. In the middle of all this, people kept getting dinner on the table and kids to bed. They did not have time to become experts in perfluoroalkyl chains. They learned what they needed, forgot the rest, and trusted their neighbors to carry the other part. A town is not a lab. It is a place where the work happens alongside the rest of life. That is why the changes that lasted were the ones that fit into routines that already existed. A note on a calendar, a habit at the sink, a preference for one package over another when the price was the same. No one traded a life for a protocol. If you zoomed in on a single house, you would see a ledger written in small lines. A pitcher filled and emptied. A cartridge replaced when the month turned. A pot used more and a bag used less. A pan taken off the flame before it smoked. A floor wiped before crumbs turned into grit. None of this is proof of virtue. It is evidence of attention. Over time, the house pays you back by carrying less of what you didn't intend to invite in. If you zoomed out to a region, you would see another ledger. A contract awarded for media changeouts on a schedule that no one will praise, but everyone will rely on. A school that tested fountains and posted the results on a sheet of paper parents could understand. A small manufacturer that switched to a different surfactant and, before the year was out, added a capture step it had not budgeted for originally because the first month's samples said it should. A health clinic that added one question to an intake form about water and one line to a handout about heating food. Quiet adjustments accumulate until a place behaves as if it learned something. The longer the story went on, the more it resisted grand claims. Exposure did not vanish. It bent. Blood levels didn't crash. They drifted and edged, and, in families that stuck with their new routines, settled nearer to the background that the rest of the country carried. That background was not zero and wasn't going to be. The point was not to win at numbers. It was to take the numbers seriously enough to make them boring. All of this ran alongside the piece that had launched the series. Refrigeration that didn't kill people and materials that didn't corrode when they touched the things we needed to make. Those gains were still real. The cost was real too. Living with both facts at once put people in a steadier frame of mind than slogans ever did. The world we built does some things exceptionally well and some things carelessly. The task is to shrink the careless parts without losing what works. There were mistakes even in the fixing. A few facilities shipped captured waste to handlers who did not meet the standard they promised, and towns had to learn the difference between a certificate and a track record. A few utilities posted numbers late and learned that silence always breeds more fear than a bad line on a chart. A few companies leaned too hard on the idea that a new chemical name erased an old responsibility. They were reminded that accountability travels with function, not branding. But there were better stories too. A small city with a lean budget met a strict limit by phasing upgrades in the right order and sharing progress without spin. A union local negotiated blood testing as a routine benefit and took the mystery out of what the numbers meant. A regional airport finished swapping foams and, a year later, posted groundwater results that showed the trend everyone had worked for. None of these made national news. They made life a little cleaner around the edges where people actually live. The language changed as the work did. Crisis gave way to program. Outrage gave way to report. No one told us gave way to here's the schedule. It wasn't that feeling had no place. It was that feeling had done its job and made room for competence. A town cannot run on indignation. It runs on calendars and parts that arrive when they should and people who remember how to do a procedure right after the person who trained them moves on. In houses where the subject had once been a dinner argument, it became a kitchen rule like any other. Don't leave the stove unattended. Don't microwave the wrapper. Change the filter when the month turns. Rinse the pitcher at the end of the week. Those sentences have no poetry in them and do not need any. They are the texture of a life that will hand better numbers to the next set of blood tests than the last set had. If you stand at a sink and watch water run, it is easy to forget every system that touches it before it reaches your glass. Pipes and intakes and beds and resins and audits and contracts, and the person who takes a sample in the rain and the person who stays late to finish a report all share the moment without being seen. A place that knows that tends to do better than a place that doesn't. It spends less time reinventing the same argument and more time keeping its promises. We started in a lab where a cut-open cylinder spilled out a white powder, and we end with what happened next. Tough materials solved real problems. Safer fridges, longer-lasting pipes, more reliable medicine. The mistake was different. We put make it above contain it and postponed the question, where does it go after? Here's the simple, honest frame. If something is built not to break down, it won't disappear on its own. Responsibility starts before a sale and doesn't end at the factory gate. What that means in practice. In manufacturing, keep the loop closed, capture air and wastewater releases, and count captured material as carefully as product yield. Publish measurements, plain numbers your neighbors can understand, not internal use only. At the water utility, pick tech that fits your water: granular activated carbon, ion exchange, reverse osmosis. Plan media changeouts in advance and post charts on time, when the line looks good and when it doesn't. Set standards at levels instruments can see and systems can meet. At home, filter drinking and cooking water, reheat food on a plate. Don't overheat pans, clean dust sensibly. Not heroics, habits. Small actions, repeated over years, shift the baseline. For firefighters, airports, and shop floors, swap foams, update gear, change procedures, and make it real in training, not just on paper. Where fluoropolymers are truly essential, control isn't strict, it's non-negotiable. This isn't panic or excuses. It's execution. When a utility installs the right treatment, blood levels drop over time. When a plant treats leftovers like product, the river stops carrying its name. When households stick to a few simple habits, the baseline falls. No, wow, just work. Here's the one line worth saying out loud. Things made to last need care, or they'll stay with us where they don't belong. We're not ditching useful materials. We're ditching irresponsibility. Specs should list right next to price and performance, environmental fate, movement in water and air, and a proven containment method. A replacement isn't a shorter chain. It's a tested behavior profile, proven before scale, not after. This video isn't about villains or magic fixes. It's about turning worry into procedure. Standard operating steps, replacement calendars, open reports, training new people. That's where trust comes from. And trust holds where numbers arrive on time, even when they aren't pretty. Bottom line, use what works. Keep it where it belongs. Make containment part of making and measurement part of truth. Hand the next glass water that's a little better than the last. If you build forever, remember, you're volunteering to be its caretaker. If you want more straight, useful stories, no panic, with enough detail to live by, stay with Midnight Paradox. Subscribe so the next episode finds you when the house is quiet. Comment with one habit you'll keep after this video. Share it with the person in your life who fixes things. We'll be here after midnight, keeping the long-lasting parts in the light.